This is the induction annealer that I built to anneal my rifle brass. And so let me walk you through this setup. I'll show you the basics of how it works, and I'll go through some details of, how much this thing cost, and I'll talk a little bit about the, the upside, the downside of building something like this. So this is an automated induction annealer. Again, I made it to anneal rifle brass for reloading purposes. It's got a little hopper and an automatic feed system. And basically this thing will cycle brass about every 6 or 7 seconds. So you can really get some good throughput on this thing. It'll really crank it out. This is actually the second version of this system that I've built. It's based on a board from a guy in New Zealand, MG&Z makes, and so I'll talk a little bit about buying that and getting it all set up, although I'm not going to go super detailed. I may make another video later, really going into detail about getting the software and everything set up, but it's just got a little platform here with a drop system linked to a regular little RC car servo. I've got an adjustment here that I can raise and lower using some 3D printer parts. I've got a Teflon block up here to hold the case in place. That way there's really no danger of that melting. At the bottom of this thing, and let me see if I can... All right, so at the bottom, you can see we've got a trap door system, and the servo will open and close this trap door. It's this thing right here, this trap door is made out of Garolite, which is a very high temperature fiberboard. And one of my goals was to get as little metal around this area as possible, just in case any stray kind of inductance heated this stuff up. I didn't want very much there. I also wanted all very high temperature components. And so that's why I went with the Teflon block and a Garolite trap door system. You can see there's some cracks in my 3D print because I didn't get my tolerances quite right on these linear bearings. So that has cracked through, but it works, and so I haven't worried about reprinting this just yet. In a perfect world I would, but for right now, man, this thing has been kind of a hassle to get all straightened out, and as complicated as it is, the platform was actually one of the parts that worked with the least amount of fuss, and so I just haven't worried about getting that thing redone. So here we've got the main induction coil, the main heater coil. This thing, I think, is either 8.5 or a 9.5 turn coil. I went through a lot of copper before I got this thing wound to my satisfaction, to my liking, with no kinks, with no problems. It was actually tough. And so right off the bat, I'll say if you're ever looking to wind small diameter copper tubing into a coil like this, my best advice, use regular kitchen salt, granulated fine ground kitchen salt. Get your tube real straight, get it annealed, fill it up with that salt, crimp each end so that it's super tight, that salt packed in there. Then you'll be able to wind that tubing without collapsing. And then the magic, get yourself some adapters to fit the tubing up to a regular standard hose bib outside the house. Then you can basically open up the ends and, again, using the fittings, attach that thing to a regular garden hose bib, open that thing full blast, and it will eventually just melt and push all the salt out. And you won't have any problems. I tried ice. I tried ice with soap in it. I tried sand. I tried a bunch of different things. And that was by far the easiest, fastest, and it actually worked. And so that's how I got this thing. And let me pop this thing off real quick. This is just a little adapter because the case is falling through here. Even though I've got it good and centered, there's enough tolerance built in that they can get a little off and bounce. You can see I've got this thing wound pretty tight, and you can tell there is no kink in this thing. It is wide open, so that allows me to water cool this loop. I want to say this is about a 3/4 of an inch, maybe 20 millimeter loop in there, and you can see it fits a case pretty good. You do want your windings to fit your case pretty tight. That gets you the best coupling. I've got a fiberglass sleeve on here to keep it insulated. The reason it's all miscolored is because during testing, I didn't have it water cooled. This son of a gun gets frickin' hot. I will show you right here. It will absolutely murder some brass, I think. So this is a regular 30-30 case, 30-30 Winchester. That looks like Remington manufacturer. This thing will melt that, I'm telling you, 3 or 4 seconds. Because I'm running 1,000 watts power supply through this thing, and yeah, I'm actually putting 1,000 watts through this thing whenever it's heating, because part of this system is I know how much voltage that power supply is running, and I've got an amp meter, so yeah, I'm fully just pulling like a full kilowatt at this end. It will just destroy some brass. So here's my control system. Let me turn this on. So I have a dual power supply set up, which I've got a 12-volt power supply and a 48-volt power supply. The 48-volt only goes to the main coil. And so everything else, all the controller, the pumps, the fans, the servo, everything else is running off of a 12-volt system, which is separate. That way I can turn on the controls and do testing and not have to have the main coil powered up, just for safety and hassle and noise and everything else. So control system, the way I've got it set, these are just some momentary switches. So you've got basically a time setting here, right? And so you can hold it down and it will reset the time back to 1 second is the minimum. You can see I've got a thermal monitor. I've got a little temperature probe in there on the main ZVS circuit. That way if it gets too hot, it'll tell me. Mode, all right, so you can go one shot, which is basically it'll just run one cycle. Free run, it will just run until you shut it off. And then this auto feed. So if I turn the auto feed, it'll ask, hey, do you have everything set the way you want? Once you get your height setting and everything up here all loaded up, and you've got everything set up to the time that you want to anneal the case, click it again, and then you say, okay, run. And so there it goes. And so it'll start feeding in cases, then it drops it down, loads it up, does the annealing cycle, and here's the trapdoor system working. And so that's how the thing works. And you can see that this setup up here is based on the design of, again, that MG&Z Makes website, the guy that designed all this. I actually redid everything myself. So this is actually not using his STL files. I, from ground up, redesigned everything because I wanted the hopper, I needed to print it on my 3D printer. His wouldn't fit. I wanted to change a little bit about the way it's set up. This is a different feeder wheel system than what he uses. So it's extremely similar, obviously based and totally copied from his design, but I wanted to change some things. And so back here, running the feeder system, I have a closed feedback loop stepper motor. And so that was total pain. I would say you really don't need to go closed loop on this. A regular stepper would really work fine. The one problem with a regular stepper is if you get a bind, I'll show you what happens. So if this thing binds up and it can't feed, a regular stepper will just stop, right? And it won't ever catch back up. If you unbind it, you'll see how far this thing wound because it's closed loop. It is constantly counting how far behind it is. Now, I don't know that that's actually helpful because if you have a jam, you probably want to just stop and reset everything. The biggest problem I had with a regular stepper motor is if this thing just binds a little and it slows down, it can get out of sync because there's really no feedback on is it interacting with the rest of the steps. So with a closed loop, it tends to push through those problems and keep in sync a little better. And one of the big reasons, by the way, that I redesigned all this is because of tolerances. The way my 3D printer was toleranced, I was constantly having to sand and get everything loosened up in here to work better. And so I just redesigned everything so that I wouldn't have to worry about tolerances much. So I'm going to turn this thing off. All right, so I'll show you a little bit about how this feeder wheel works. So you can see it's got 3 positions. I'm gonna power this thing down so I can turn this freely. So once it's powered off, you can just spin this thing pretty easy. So one of the nice things that I did is I made little magnetic blockers that just snap in place for different size cartridges. And so each one of these things is sized for slightly larger or smaller brass. If I slide this thing in there, right, it just snaps in place. And so you can easily modify this to use different calibers and stuff. So you can easily adapt this thing to different calibers. And what you want to do, the way it's set up, is right now the servo system, that closed loop stepper, it doesn't know where it is. So like if I want to switch over to a smaller caliber, I pop this out, then I'm going to center right there on this smaller caliber. And so basically now, whenever that system wakes up, it's going to think that's 0 position. All right, so now I've got it fired back up with that new 0 position. Get it going, and you can see now it's going to function with a different position on that thing. So you can easily go from like 223 brass to moderate 6.5 to larger cases pretty easily with this feeder wheel design. And, you know, it's very fast. The only thing, you do have to keep track of these little plugs, just so you make sure that, you know, you're on the right one and that you don't lose one, because then you'll get cases falling in and binding up. It's also got this little blocker up here. This is just, you know, if I had it to do over again, I would have just built this into the 3D print. This is just to keep cases from binding right at this point, because there tends to be a little bit of an opening there that cases can get hung up and try to double feed. So this just blocks that off. Right now, again, once this thing is turned on, that closed loop stepper is going to constantly stay indexed. You can actually hear the power supply ramping up, trying to give it more juice. It's constantly going to set that as the home position, right? So really easy with this feeder system to move to different sizes. All right, so you know, that's the setup here. Again, I don't think I mentioned this is just the start-stop button on all this. So let me show you a little bit of the inside. So I've got this thing in a regular computer case that I have kind of completely just drilled holes and carved up with Dremels and stuff like that. So let me open this up. I'll show you the insides. Okay, so here's the inside of the system. I know it looks pretty raggedy in here. This was one of those projects that took a long time and a lot of work, and once it worked, I was kind of burnt and done. So up here, just the wiring. I've got these loose just in case I ever want to reuse these switches. I didn't trim all the cable from the hook in, but I do have them so that I can just disconnect the switches and easily take this stuff out. There you've got the main coil coming in. This is the ZVS board. This I made myself based on a design from a YouTuber, a guy named Schematics. Really, really helpful dude. On his website, he's got a forum, and he's pretty involved. And so I asked him several questions about getting this thing set up. And so you've got a bunch of capacitor bank. You've got a couple of big MOSFETs in there. Big inductors. These suckers are about 10 bucks a pop. Then you've got some resistors and stuff. Really easy to make. The mounting hardware that I'm using are these lay-in ground lugs, and they just bolt in, and then I've got them tied in. Here you can see the bottom. You can see I've got super heavy solder. Well, that's actually like 10 gauge copper, stranded copper that I've soldered into a big rail. And so then you can see up here, I've got a couple of connectors that go and attach under here. So this is actually very secure. Physically, it mounts up very solid, rigid, and it's really easy. You can see I just unscrew this and it just rolls that right out. And so you can easily take this coil in and out without damaging the copper while maintaining a very solid connection, both mechanically and electrically. So I went with that system. It's not cheap because these little ground lugs are, I don't know, $5 a pop. They're solid copper, but I don't have to worry about anything burning up or being able to handle the power that I'm running through. Because as you can tell, this is a big old chunky boy. It's, you know, I think he rates this thing as 1.4 kilowatts. So 1400 watts of power this thing's rated for, and I'm running 1000. And here's another look at how the mechanical connections, I've got, you know, these things running in here. This is the ground lug. I've got the main power coming in over on that side. That is controlled by, right back here, kind of hard to see. Right there, you can see the Cridom solid state relay. This thing is rated for 40 amps. I'm only running 23 through it from the power supply. There's the control wires coming from the controller board. Controller board is down here in the bottom in this case, which probably doesn't show up very well. That is a, just a 3D printed case for the controller board. This cable, this broad white cable, that's for the servo in the feeder wheel. This orange wire controls the drop servo. The drop servo is actually powered, you can see a couple wires back there, off of, behind this panel, there is a 5-volt step-down converter from the 12-volt power supply to give extra power on the 5-volt side for this drop servo in the front. Because whenever I was running it off of the Arduino-based board, I just wasn't getting enough power. You can see this kind of copper shielded. I kind of home shielded this wire. I don't know that that ended up being necessary, but since I'd already made the cable, it just got left, and that actually goes up to the display, right? So this display is very sensitive to interference, and this big ZVS circuit switches somewhere around 100,000 times a second, 100, or 100 kilohertz or whatever. And so you get some high frequency noise, some RF or EMF, I don't know. But I was having some problems with it shutting off my controller circuit. So I was trying just a bunch of different grounding strategies and shielding strategies. I've also got a water cooling loop, right? So I've got some on-off valves so I can disconnect it without having to drain everything, but that goes to this little radiator that comes out the back to cool. That goes right into the 5mm OD copper tubing that I use to wind the main coil. Inner diameter on that is about 4 millimeters. I get pretty decent flow through that thing. And when this thing's running, again, I'm putting a full 1000 watts through this loop, and you can touch this thing with your finger. It does not get hot. Now, you don't water cool it, it will absolutely melt fiberglass. So it'll get real hot. It's putting out the power, and you can actually, this water cooler, whenever it's running, you can feel it back here at the fan, really getting, not crazy warm, but you can definitely tell it's doing something. The other thing in here, there's a couple of just regular PC fans that I grabbed out of some other stuff to help cool this circuit. On top, to monitor the thermals, I've got this probe that I've got, I've got siliconed in there. I had some tape just holding it while the silicone dried, so that should be fine. Now to remove, but I've just got it on there, and I've tried to snug it up to the MOSFET heat sinks because I want to monitor the temperature of the heat sinks and the MOSFETs, and I'd also like to monitor the capacitors to make sure I'm not heating anything. But this thing does temperature regulate, and it's got a shut-off programmed in. I can't remember how high I've got it set. I think I've got it set pretty high. Everything in here is rated for like 100 Celsius or 105 Celsius. So as long as it doesn't reach the temperature high enough to boil water, it's fine. Currently, the highest temperature I have seen is 38 Celsius, which is about 100 degrees Fahrenheit, meaning I ran like 40 cases in a row, and you could just put your finger on this. It was 100 degrees, like body temperature. It does not get hot. This thing is a beast. The circuit design that this guy made is completely capable of handling its rated power. Now let me contrast that, and I will show you why I'm using this circuit. I will show you the original ZVS tank that I had in here. All right, so I'm not going to pretend to be the smartest guy in the world, but let's look at the parts that I originally had put in this thing and that did work, but had some issues. So this was the original ZVS heater circuit. I got this off of Amazon. Now look, the Amazon ad says this thing's rated for 1,000 watts, but that is absolutely false. It won't blow up if you put 1,000 watts to it, but look at the power connectors. You can't even get a wire capable of holding, 20 amps in there. And again, typically 40, the higher voltage, right, the lower amps you're going to run. So I'm running a 48 volt power supply to minimize the current that I'm trying to push through. And this thing, you can't put wires in there that will carry 20 amps very easily. You kind of got to rig it up to even get the wires in there. Then it's got these little binding post things, and you can see how they're kind of discolored because I was actually cooking the connectors on this thing running my power supply. So this circuit would overheat within about 5 cases. And that means overheat, I think it was like 60 to 80 Celsius. This thing would get there in about 5 cases, maybe 6. This one, and again, for size comparison, quite a bit beefier. This one, I've ran like 40 cases in a row, and it's, body temperature. It just doesn't get hot. Now, the other thing that was kind of dumb, I was running this as my main coil design. It actually worked really well, but look how small it is. This is 1/8 inch tubing. The ID is like a millimeter. It's really small. You couldn't get much water flow. And so this would actually boil the coolant in the lines while it was running. And so that was a problem. That would end up with vapor in the cooling lines. It was just a problem. This coil was just way too small to handle the power. Now, this kind of stuff is what the MGNZ recommends, but he only recommends like a 600 watt main power supply, and I'm running 1,000, and so these just aren't capable of handling the kind of power that I was trying to put in. So, that's on me. That is definitely not on that guy's recommendations. His stuff probably worked. I was just killing the ZVS circuit, so I rebuilt it with much heavier duty stuff. And so that's what I've got here. So that's the inside. There's some stuff on the back of this panel that I'm not going to show you. Number one, because it's embarrassing because of how ugly some of the rat's nest wiring is behind there. The others, because there's really just not that much left to see as far as what's really going on in the system. The only other thing is showing you the main power supply, which is down the bottom. But again, it's just a power supply. It looks like this one, but it's bigger. It is a Meanwell power supply, so it's pretty high quality. I got it off of eBay. This one is just a cheapo 300 watt Amazon power supply that I got for about 25 bucks. And then there's the controller board, which is in here, but it's all enclosed in a shielded little case because I shielded everything down there with copper foil and then grounded it. And I don't want to open that up because it's kind of a pain, and I can show you photos of all of that. And so that's the guts. That's how this thing works. Essentially, that controller board tells the solid state relay to open or close whenever you want to do your induction heating. And it's controlling the servo motor and telling it what position to be in and when. And it's controlling the little drop gate down here. And so with these buttons, it just, turns it on and off, gets your settings. It displays up here. Current, because again, I do have a current sensor wired in down there. By the way, with these systems, usually you are running 20 amps with most of these, depending on what type of power supply. If it's a 24 volt or 48 volt, you're probably running 15 to 20 plus amps through this ZVS circuit. And so any current sensor, you really do need kind of a beefy one. I will say the recommended current sensor from this build guide that he puts out, I think is a little weak. The connectors are only rated for like 10 amps on that thing. And so even though it's supposedly rated for 20, I just didn't buy it. So I got a much heavier duty current sensor. But yes, this thing, it displays temperature, current through the circuit, time adjustment, and all this thing through this little OLED display. I still have the protective plastic on it. And that's the setup. So I'll run some cases through this thing and show you how it works. And yeah, it's been pretty great. And now that I've got it finally up and running with the new equipment, man, it's a beast. It'll do it. All right, so let's get this thing powered up. I got it closed back up now. So I 3D printed this little panel, and like I said, I've got 2 power supplies, and so I actually have independent switches for each one. This is for the controls, the 12-volt system. This is for the high power system. Whenever I flip this on, you're gonna hear it fire up. Quite a bit more noise out of that one because it's got a couple of really powerful fans to help keep that power supply at the bottom cool. The other thing I would say before I go forward, because we're about to toast a case up, I've kind of, I've mentioned multiple times, it's a 1,000-watt power supply. It's super fast, super powerful. I 100% do not recommend that you go for a 1,000-watt system. It's overkill. You will see how fast it roasts a case. It's just unnecessary, and the difference between a 1,000-watt high-quality power supply and like a 600-watt high-quality power supply, it's a lot more expensive to get the 1,000-watt or higher power supplies. And it really doesn't make that much of a difference. You're going to end up, heating this case up maybe a second faster, maybe a couple seconds. It's really not that big a deal because, look at what you're heating. It's super thin. There's not much mass here. You do not need that crazy amount of power. I did it because I got a good deal on that power supply. I don't know. I guess I was just excited about it. And so I built the system to be able to handle that. But it's not necessary. So here I'm going to turn this thing up. Let's go to 2 seconds. I don't want to overdo it because I'm not trying to melt this case. This is a 30-30 piece of brass. And so 2 seconds, let's hit it. So it didn't quite begin to glow, so let's go a little bit more just so you'll see. Okay, 2.5 seconds. There you saw it just begin to glow, right? Now, if we go much more than that, so let me get one more, and again, this is just 30-30 brass because I've got a bunch and it's old and it's cheap. If we go much more than that, just go a 0.3 more seconds, you'll see how bright this thing gets. Right, so it will absolutely nuke a case. If I go just a few more tenths of a second, it will start to melt one. Which I found out, you can see that one right there in the middle, down there at the bottom, where I melted that neck, right? So this thing, it works real fast. And I guess the last thing, let me see if I can find one of these cases that's not hot. Yeah, so let me put this thing in. All right, is what kind of power this thing runs whenever it's hitting one of these cases. Again, I mentioned I've got a thermal monitor, that little temperature probe in there, currently 26 degrees Celsius. So let me turn this down. I don't want to get them that much. Let me just give you a couple of seconds rather than getting that case near its melting temperature. And so you'll see when this thing runs, it actually monitors the current live. All right, so again, I'm running 22, 23 amps. So it's a 48 nominal 48 volts power supply, and so that's clearly, again, pulling its rated power. Now, I do think I've got it turned down maybe to like 45-ish volts. I could turn it up, and I think it'll do as much as 50. It's got a little adjustment on it that you can slightly tweak the voltage. But I'm not really having any problems, so I don't know that I'm going to mess with it from here. I'll probably just leave it. Yeah, so that's the basics, and it works, and I'll put in some footage of me getting it set up on a case to actually do some real annealing tests and running some cases through it. All right, so I've got 10 cases loaded in here. We'll run this a quick cycle. Okay, so let's set this thing over to auto feed. I'm gonna turn on the power supply. So the way this thing is going to work, and actually, now that I forget, I actually have to put a little feeder tube here to make sure that they go into the coil. 1 second. All right, so I've got that additional tube there that'll feed a little bit more reliably. So we'll run this cycle. I've got it all fired up, got the power supply on, so here we go. All right, there we go. See my probe in there, still 27.5 degrees Celsius. So the circuit seems to be doing fine, not getting too hot. That thermal probe is right there on those capacitors, right next to the heat sinks on the MOSFETs. And here you can see my estimate for how much I've sank into this thing is $850. Now, to be honest, I spent way more than this because I didn't include all the things that I tried and that I tore out and redid and got, better stuff. Like, I bought multiple kinds of servos, bought a couple different kinds of servos, and I originally made my induction coils with smaller diameter tubing, and I used an Amazon ZVS circuit that ended up getting way too hot, and I couldn't run it consistently. And so there's a bunch of stuff that I've redone that I didn't put into this, but I'm sure I spent another $100 probably on just crap that I tore out and replaced, and found out, nah, that's not really what I need to do. And I mentioned I tried to cast some stuff out of RTV silicone at one point. Well, I spent money on that silicone. I spent money trying to encase the induction coil into different ceramics to try to keep it protected and keep it insulated, and just all kinds of different stuff I tried that I wasted money on. So now I can give people good advice about what not to do, and I'd say, like, if you're good at electronics and soldering, dude, just use this guy's circuit. It works so much better than the ones you get on Amazon. It's not cheap. If you actually filter this for how much I spent, $150 just on this circuit. But let me tell you, the thing is an absolute beast. I can run 40 cases in a row and the thing doesn't get above 100 degrees Fahrenheit. Like, you can literally leave your hand on it and just anneal cases continuously, basically. It handles 1,000 watts with no problem at all. And I mean, like I said, I can melt cases in 5 seconds. It's kicking out so much power real quick. Probably not even 5 seconds. I think a 30-30 case, about 3.5 seconds, and that thing is literally melting. So $150 just sunk into the ZVS board, but yeah, I should have just started there. Would have saved a lot of money. So that's the list of parts, just in case you're wondering, what's involved, what kind of cost you might be looking at. I would say, my conclusion, looking at this and looking at how much time and effort and design, unless you just really want a project to mess with, just buy an amp annealer. Yeah, you're going to spend twice as much to get an amp annealer, to get it all set up. You'll spend way more money, but good Lord, have I put so much time and effort into getting this thing to work, which is kind of cool, but it probably still doesn't work as well as an amp does. $1,500, you can have an amp annealer. Now, it won't be automated. Mine is automated, so I guess, technically, it costs half as much, and mine is automated. And if you want your amp annealer automated, it's another $500 to get their little case loading system, because I will say the amp annealer design is not the most efficient design from a mechanical perspective. The way it loads in that brass does not, it's not very conducive to automation. But it works like a hot damn. And you've got support from a company that is full of very smart and capable people should you have problems. Mine, whenever my crap breaks, I've got to really figure some stuff out, and it's had some problems. It's had some teething pains, so it's been a fun project, but it's not like it's been great. As far as from an ease of use perspective, I have tracked down a bazillion gremlins. I have gone through multiple revisions of every system in there just about. So whether it be the ZVS circuit or good Lord, I bet I've wound 10 to 15 different main heater coils of a variety of different designs, and I've wasted, probably $100 worth of copper tubing just crushing stuff, breaking stuff, messing it up, trying to figure out exactly how you can bend it without kinks and all kinds of stuff. So, yeah, there's one thing to be said for that amp. The damn thing just works. All right, well, that's going to finish up the overview of this induction annealer. If you've got any questions or want me to expand on anything, just leave a comment down below and I'll get back to you. Thanks.